Welcome back. So, in today's video lecture, we will look at the Gibbs adsorption isotherm. In this lecture, we will come to know that how Gibbs adsorption isotherm equation will help us, determine the surface excess. Okay, by knowing the data like the change in surface tension. With respect to change in concentration. Let's say you have a data between surface tension as a function of concentration. Uh, if you can get the slope of that, let's say for example d gamma by dc, based on that information, can we calculate surface excess of solute? Okay. So, that is what we are going to look at in today's video lecture. We will derive the Gibbs adsorption isotherm equation for a general case. Then for we will deduce for a binary case how the equation can be simplified, and based on that how one can calculate surface excess. That is what we are going to look at in today's video lecture. Let us begin. So, as we discussed in previous class, whenever we deal with the bulk phases, let's say we have alpha phase and we have beta phase, right? These two are two adjoining phase. Let's say we have some solute molecules present in the respective alpha phase or beta phase, but one of them may be having a tendency to adsorb, or sometimes both of them may be having the tendency to adsorb at the interface. Remember, this surface is present as a additional phase, right? So, if they have a tendency to absorb, some of these molecules would go to the interface, right? So, they will be confined within this zone of interface as well. Okay. So, when we refer to surface excess, we know that surface excess is defined as gamma, which is a Greek letter, as n by a, right. So, n here is the number of mole and a is the area. Okay. So, interfacial area. Now, we know that because they have got tendency to adsorb, so one can actually derive to show that how the Gibbs adsorption isotherm or adsorption isotherm will be function of surface tension and concentration itself. Okay, the concentration that we employ in the bulk phases, okay, and gamma is the surface tension. So, that is what we are going to look at. So, in previous lecture we also looked at the how the for some cases, let's say if you measure the property as a function of distance across the interface, right. So, if you are going from one bulk phase to another bulk phase, because the bulk phase that we refer to are homogeneous phase, you do not expect any sort of fluctuation, but when they are nearing the interface there will be a fluctuation, because the property will be when they are approaching from one phase to another phase, there will be some fluctuation near the interface, that is expected. So, this profile can be sometime linear or sometime exponential, okay, or sometime it can be any asymmetrical distribution, asymmetrical profile, but we have what is known as the Gibbs dividing plane, which is nothing but identifying the imaginary plane or reference plane as proposed by Gibbs, Gibbs dividing plane, I mean as indicated by, as defined by Gibbs dividing plane. So, in this case what one can do is by identifying the midpoint, you can actually create the imaginary interface, right. So, imaginary interface. So, we do not know where exactly interface lies, right, because there is a fluctuation as and when it approaches the interface. So we don't exactly where exactly the interface lies, right. So for that, to avoid that conflict, one can identify the midpoint such that the distribution, right, towards the right side, towards the right and towards left, both will vanish, right, because there will be no overestimation or underestimation. Okay, there will be equal distribution. So in such case, you can say that this point is my interface, imaginary plane or interface now, right. So once you identify that, it is easy to say that the surface excess for one of the components is 0. For example, if you have solvent, if you deal with the binary mixture, you have solvent and solute. There are two components, right, in the mixture. For solvent, because solvent is usually present in a very large quantities, they will one would end up with the symmetrical profile always, right. In such case, it is easy for us to locate the midpoint, so that there is no positive surface excess or there is no negative surface excess, because one would achieve uh, so there will be no net surface excess in that case. So one can say that the surface excess for solvent in that case is 0. So that is the idea of using the this Gibbs dividing plane concept. Okay, so we are going to look at the Gibbs adsorption isotherm, and we will come back to this uh, graph again, and say how we can make use of the Gibbs adsorption isotherm, at least for a binary mixture, how we can easily reduce the determine the surface excess, right, by knowing the information such as surface tension and concentration, right. Yeah. Okay, so our equation, our the starting point is going to be Gibbs equation itself. So whenever we define Gibbs energy, so you have so three phases here, right. One is the alpha phase, okay, one bulk phase, and the other one is the beta phase, another bulk phase. You also have additionally interface, right, that is sigma. So the sum of these energy, Gibbs free energy, is going to be total Gibbs free energy, right. So this is going to be our starting point. Now if we have to define for a general case, we know G is nothing but H minus Ts, enthalpy and entropy. This is going to be temperature, right. This is for a pure component, right. This is for a pure component. Okay. So this we can break down enthalpy further into U plus PV. This is actually uh, PV work, right, minus Ts, right. This is again for a pure component. If you have to express this explicitly for mixture, let us say uh, if not for a pure component, for a mixture, we can express this equation in a similar fashion, but additionally you will have what is known as the summation I n I mu I. So this term, additional term, will also come into picture. Now if I have to define each bulk phases separately, individually, how I can mention that. So that is what we are going to look at. So G alpha is going to be my bulk phase 1. So in such case, I can define this as alpha, right. Yeah. So alpha, okay. So this is going to be my U alpha plus PV alpha minus TS alpha plus summation I n I mu I alpha, right. So similar way, you can also define for another bulk phases, that is beta itself. So you have U beta phase PV beta minus Ts beta plus summation I n I mu I beta. Okay. So these two cases, if you look at, G is function of T, P and N, right. So, based on this you can write the Gibbs free energy equation for these bulk phases, whereas for sigma, which is interface, you can also express this explicitly for the another boundary, that is interfacial boundary. So, you can say that as U sigma plus PV sigma minus TS sigma plus summation I N I mu I sigma. Remember, in addition to TPN for interface, you also have what is known as area, which is also important, right, interfacial area. So, you have, it will be function of temperature, pressure and the number of moles and area as well. So, you will also have what is known as gamma A, this is actually surface tension work. So, you have to include that. So, if I look at these two phases, this alpha and beta phases, these terms are quite common, I mean are common, whereas this is distinct, right. This is distinctly this is only the case for the interface, right. So, G sigma, right, this is very distinct for the interface, correct. Yeah. So, you can now you can express this in terms of differential. Okay. When you express this in terms of differential, now since you know alpha, beta and sigma, these are going to be common in all these cases. So, I can simply express this as alpha, beta and sigma, which is nothing but du. I do not need to now specify or denote whether it is alpha, beta, because this is going to be summation of all these three, right. So, I can simply mention this as du plus PV, which means that I am sorry. So, I have to derive this, right. So, it will be du plus P dV plus V dP minus, so we are actually deriving. So, P dV, PV will be P dV plus B dP minus S dt minus TDS, okay, plus summation I N I d mu I plus summation I mu I d n I. So, you have this additional term which will not be put inside this bracket, because this is only applicable for the interface. So, you can write this separately as gamma dA plus A d gamma, right. So, this is what we know. Now, we can define from the first law of thermodynamics, we know the change in internal energy can be defined as del Q plus del W, right, which is the work done. Okay. Remember, for reversible process, we know from the second law of thermodynamics, delta Q for reversible process will be TdS. Okay. And for work done for reversible process is usually minus PdV. Okay. And also additionally, you will also have work done associated with the non-PV, right. So, you can also say work done associated with the non-PV work, right. Okay. So, non-PV means it can be shaft work, surface tension is also a non-PV work. Okay. So, remember, we have denoted this with minus here, because we have to use the sign convention, positive if work is done on the system, negative if the work is done by the system, but this minus takes care of whether the work done on the system or done by the system. So, you do not need to worry really whether you have to put plus or minus or not, right. So, you do not need to put plus or minus, because for when you generalize equation, you can simply use this minus PdV minus delta W non PV. So, if work is done by the system or done on the system, this sign automatically takes care of that, right. Yeah. So, we will just substitute this back into the equation that we have just now obtained. So, you have alpha, beta, sigma Now, if I put this back into this equation, TDS minus PDV minus delta W non PV, okay, plus PDV plus VDP minus SDT minus TDS, okay, plus summation I Ni d mu I plus summation I mu I dNi plus gamma dA plus A d gamma, right. So, remember, since there is no shaft work involved in this example that we have described, so you can actually equate this delta W non PV to the surface tension work, which is nothing but gamma dA, right. Okay, in the absence of any shaft or turbine, you can equate this non PV work to the surface tension work. So, in that case, this term and this term can be cancelled out each other, okay, right, can be cancelled out. Now, we can see that this TDS term also cancels out each other. Then you have minus PDV plus PDV. Okay, so you will not have much of this term. So you will have simply very few terms now. That is nothing but VDP minus SDT. Okay, plus summation I Ni d mu I plus summation I mu I dNi, okay, plus A d gamma. So, this is what we have. Now, at constant temperature, okay, let us say we assume at constant temperature and pressure, and also for a closed system, okay. So, for a closed system there will be no mass transfer, right. So, you can assume that dNi will be 0 in such case. For constant temperature and pressure, you will have this term also cancels out each other. So, you will have also have this term, right, cancelling out each other, I mean cancelling out equally, right. So, in that case you will be left out with the simply summation alpha, beta and sigma. You will have simply Ni d mu I plus A d gamma, right. Right. So, at equilibrium, right, we know that at equilibrium dg is supposed to be equal, okay, right. So, in such case this is one, right, this is one condition that we have. The another essential condition that we know is the from the for the mixture that is alpha and beta, these two are bulk phases. So, for the mixture from the Gibbs-Duhem relation, we know that Ni d mu I is actually 0, okay. Whether it is bulk phase 1 or bulk phase 2, this is true for the from the relationship that we know already, that is nothing but Gibbs Duhem equation relationship, right. Okay. So, but what is now left out is we have only one term that is not 0, that is the from the surface, right, from the interface. So, you will have Ni d mu I plus uh, you know uh, ga d gamma A, right. So, A d gamma, which is equal to 0. So, this is the term that we have. This is these two terms only will survive now. So, now what is the d gamma then? In that case will be, you will have summation I Ni d mu I divided by A, right. So, this will be minus. So, now in that case you know what is d gamma, which is nothing but minus summation I gamma I d mu I, right. So, this is actually going to be my surface axis. Okay, this is my surface axis. So, this is only one part of the equation. Now, what we can do is we can further simplify this equation. Let us say if we assume for the case of binary, let us say if we assume for the case of binary mixture, okay. So, you can explicitly write this equation as you can write this equation as so this is going to be d gamma, okay. So, d gamma is going to be minus gamma 1 d mu 1 plus minus gamma 2 d mu 2, right, d mu 2, okay. So, this is for the binary. Remember we have just when we begin deriving, we have just introduced the concept of the Gibbs dividing plane, right. So, Gibbs dividing plane, whenever you measure some property, okay, as a function of distance, okay, you have one adjoining bulk phase, and near interface the property that you measure will fluctuate, but uh, if you choose the components such that they will display the symmetrical profile, okay, no matter whether the fluctuation is small or large. So, if you are able to find out the midpoint, which is something like this, so this is going to be my imaginary interface, right. This is going to be my imaginary or new interface. So, I have located my interface such that there is no surface excess here. So, if you just sum all, that is the whatever the surface excess you have towards right, whatever the surface excess you have towards left, both will cancel out each other. So, in such case you can say there is no surface excess for the case of solvent, which if I denote as gamma 1, which will be 0, okay. So, that is what we are going to so that is the advantage we have when we choose the exact location of the Gibbs dividing plane, right. So, in the case of solvent, because it is present in a very large quantity, you will always get the symmetrical distribution. So, it is easy for us to equally divide, right. So, then you can say the surface excess is always going to be 0 for solvent. So, in such case you can obtain this gamma equation something like this. It will be simply minus gamma 2, okay, d mu 2, okay. Yeah. Okay, right. So, now what we can do, we know what is the d mu 2, right. We know what is d mu 2. So, we know from the mixture d mu I is going to be, okay, R T ln, okay, F I bar by F I, okay. So, here we know what is the d mu I, okay, for a mixture. We know the change in chemical potential for a mixture, which is nothing but RT ln Fi bar by Fi naught. This is the fugacity of mixture for any desired condition, and this one is fugacity for a mixture at any standard reference state. Okay, so you can also explicitly denote the R Fi bar by Fi naught as ln AI, which is the fugacity, right? Fugacity itself, right? Okay. Now we know for solute molecule itself, if I have to deduce the change in chemical potential, I can simply write this as d mu 2, which is nothing but RT ln, okay, A solute, right? Okay. So we can also express the activity sometimes as in a concentration units as well. So in that case you can simply represent this as C, which is the solute concentration in this case. Remember, whenever you substitute the value in concentration, you have to understand that it has to be normalized with respect to some reference state. Okay, if it is not given, then you can assume it as 1, right? Or you should always normalize the concentration with some standard reference state, that is nothing but like C by C naught, right? So which means that, let's say if you consider surfactant mixture, okay, so surfactant plus let's say you have surfactant plus water, right? This is one case, and you have water as a pure component also, right? So you have also water as a pure component. In that case, uh, so you have to normalize with respect to the pure water, right? In this case, C naught will be pure water. Let's say if concentration is expressed in terms of N by V, that is moles per liter. For let's say if you are dealing with 1 liter, then you know how to express the get the the C, how to normalize the concentration with concentration based on the pure reference state will be like you can calculate this by knowing the N by V. For 1 liter of water, you know that this is going to be number of moles. So 1 liter meaning it is 1000 gram. So if you divide that with molecular weight, that is 18, okay, divided by volume is 1 liter here, again this is going to be my 55.5 moles per liter. So whenever you deal with substitute concentration values here, solute values here, we should be normalized with respect to this, that is 55.5 moles per liter. If it is not specified, you can assume 1, right? So that has to be noted down, right? So we can also express this in terms of RT D ln C, okay, because this you can express as dC by C, which is nothing but ln C, okay, which is nothing but ln C. So if you substitute this back into your equation, that is d gamma equal to we have this equation, right? So minus gamma 2 minus gamma 2 d mu 2, right? If I substitute this equation in this will be simply RT d ln C, right? So what is going to be my then surface excess will be minus 1 by RT, okay? You will have d gamma by d ln C. You can also express this in terms of minus C by RT d gamma by dC. So this is for solute, right? Right. So this is our Gibbs adsorption isotherm equation for solute molecule. So by knowing the information such as the d gamma by dC at specific concentration, you can actually measure what is going to be your surface excess per solute. We will stop here. We will continue from the next lecture. Thank you.